Hey science fans and curious minds, welcome to our deep dive into the strangest, most counterintuitive phenomena in physics. We'll explore 10 effects that defy everyday logic, shake the foundations of intuition, and push researchers to the edge of what they understand. No dense equations, just clear explanations, real experiments, and the big questions that remain. Buckle up, here we go! The quantum Zeno effect, what happens? A quantum system that would normally evolve into a new state can be frozen in its initial state if you measure it frequently enough. Each measurement collapses the wave function back to the starting point, preventing the change. Why it baffles us in daily life, checking your oven doesn't stop the cookies from baking. In the quantum realm, the act of observation is an interaction so powerful it halts natural evolution. Real-world tests and uses demonstrated with ultra-cold ions and rapid laser pulses, vital for protecting qubits in quantum computers against decoherence, keeping them in the desired state longer. Schrödinger's cat and macroscopic superposition, what happens? In Schrödinger's famous thought experiment, a cat in a sealed box is simultaneously alive and dead until you open the lid. It illustrates that quantum superposition could, in principle, apply to everyday objects. Why it breaks logic, we never see half-live, half-dead cats. Yet at the atomic level, particles exist in multiple states until someone measures them. Where exactly does the quantum end and the classical begin? Progress so far, superpositions have been shown for molecules of thousands of atoms. The challenge: environmental interactions, decoherence, destroy superposition almost instantly unless ultra-isolated. Quantum tunneling, what happens? Particles can pass through an energy barrier, even if they lack the classical energy needed to climb over it. They tunnel through as a consequence of their wave-like nature. Why it astonishes, imagine a ball rolling at insufficient speed to surmount a hill, yet appearing on the other side. That's everyday reality for electrons and other quantum particles. Technological impact foundation of modern transistors in every processor. Underpins the scanning tunneling microscope, which images individual atoms by measuring tunneling current. Quantum entanglement, what happens? Two or more particles share a single quantum state. Measuring one instantly determines the state of the other, no matter how far apart they are. Why it spooks you? Einstein called it spooky action at a distance. It seems information about one particle's state travels faster than light to the other, violating relativity. Yet experiments confirm it happens every time. Frontier research entangled photons have been separated by hundreds of kilometers in open space tests. Basis for quantum key distribution, promising unbreakable encryption in a future quantum internet. Vacuum fluctuations and virtual particles, what happens? Even empty space seethes with activity. Pairs of particles and antiparticles pop into existence, then annihilate in the blink of an eye. Why it's surreal? We think of a vacuum as nothing. Yet it's a roiling sea of virtual particles that influence forces and energies throughout the universe. Experimental signatures. The Casimir effect. Two metal plates in a vacuum attract each other due to altered vacuum modes. Lamb shift. Tiny shifts in hydrogen energy levels directly attributed to vacuum fluctuations. The black hole information paradox, what happens? Anything that falls into a black hole seems to lose its quantum information forever. Yet Hawking radiation implies black holes evaporate, so information must escape, creating a conflict between quantum mechanics and general relativity. Why it's perplexing? Quantum theory forbids information loss. Relativity says nothing can escape the event horizon. Reconciling them remains one of the greatest challenges in theoretical physics. Leading ideas. The holographic principle. Information is stored on the event horizon's surface. Firewall proposals. Spectacular energy barriers just inside the horizon that might preserve information. The arrow of time and entropy. What happens? Microscopic physical laws are often time reversible. Yet the universe moves inexorably from order to disorder. Entropy increases, and we only remember the past, never the future. Why it's mind-bending? Why do shattered glasses never spontaneously reassemble? Why does heat flow naturally from hot to cold, never the reverse? The ultimate origin lies in the extraordinarily low entropy state of the Big Bang. Current exploration and cosmological initial conditions explain the universal direction of time. Research probes links between gravity, quantum mechanics, and thermodynamics to clarify why time has a single direction. Ghostly neutrinos, what happens? Neutrinos are nearly massless, neutral particles streaming through space and us by the trillions every second, rarely interacting with anything. Why it's amazing, originally thought massless, neutrinos were discovered to oscillate between types, proving they have mass. Yet they barely leave a trace, making them notoriously hard to study. Detection efforts, massive detectors in deep mines and Antarctic ice cube, capture rare neutrino interactions. Solar and supernova neutrinos offer windows into stellar processes and fundamental physics. String theory and hidden dimensions, what happens? Instead of point particles, the universe's building blocks are tiny vibrating strings in up to 10 or 11 dimensions, most of which are compactified beyond everyday perception. Why it seems fantastical we live in 4 dimensions, 3 of space, 1 of time. Where are the extra ones? Why don't they show up in experiments at current energy scales? Theoretical status, Large Hadron Collider searches for signs of extra dimensions in high-energy collisions. Mathematical breakthroughs describe Calabi-Yau manifolds where hidden dimensions curl up. The many worlds interpretation, what happens? Every quantum event spawns multiple branches of reality, one for each possible outcome. All branches exist simultaneously, but observers experience only one. Why it's staggering? It implies an unfathomable number of coexisting universes, each hosting a version of you that made a different choice. We can't access these parallel branches, but mathematically it avoids wave function collapse. Debate highlights, favored for its internal consistency and simplicity, eliminating the need for an external observer. Critics note the lack of experimental distinction from other interpretations, branding it more philosophy than physics. That wraps up our whirlwind tour of 10 physics phenomena that defy common sense. From particles frozen by observation to hidden dimensions and quantum worlds galore, these effects remind us how much we still have to learn. Which phenomenon blew your mind the most? Drop a comment below, hit like, subscribe for more mind-bending science, and share this video with fellow curious minds. Thanks for watching and stay wonderfully baffled.